Optimization algorithms. Performance comparison optimization algorithms form the backbone of modern problem-solving in mathematics, computer science, and engineering. These algorithms determine the best solution from countless possibilities, whether minimizing costs, maximizing efficiency, or refining complex systems. Their significance spans industries, from training neural networks to optimizing supply chains. Choosing the right algorithm can mean the difference between success and failure in any computationally intensive task. Understanding optimization problems and their types. An optimization problem involves finding the optimal value of a function subject to certain constraints. This function, often called the objective function, represents the goal, while constraints define feasible solutions. Problems can be classified as unconstrained or constrained. Unconstrained problems seek global optima freely, whereas constrained ones require adherence to boundaries or conditions. Objective functions may also vary in complexity, ranging from simple quadratic equations to highly nonlinear and stochastic models. These variations influence which algorithms perform best. Constraints themselves come in diverse forms, including equality, inequality, and integer restrictions. Handling these efficiently is crucial for accurate results. Unconstrained optimization focuses on finding extrema without limitations, ideal for theoretical modeling or scenarios with few barriers. Constrained optimization incorporates limits, essential for real-world applications like resource allocation or structural design. Gradient-based versus derivative-free methods. Gradient-based algorithms rely on calculating derivatives to navigate toward optimal solutions. They excel in smooth, continuous landscapes where gradients provide clear direction. Methods like stochastic gradient descent, SGD, and Newton-Raphson iteratively adjust parameters using derivative information. However, they struggle with noisy or discontinuous functions. Derivative-free methods, such as Nelder-Mead simplex or evolutionary strategies, avoid direct computation of gradients. Instead, they explore the search space through sampling or random perturbations. These methods are robust against noise but typically converge slower than gradient-based alternatives. They remain vital for black box optimizations lacking analytical expressions. Pros of gradient-based, rapid convergence, effective for well-behaved functions, widely supported in deep learning frameworks. Cons of gradient-based, vulnerable to saddle points, requires smoothness assumptions, sensitive to initial conditions. Popular algorithm categories and their strengths. Linear programming solves optimization problems with linear objectives and constraints. It's foundational in operations research and economics, offering guaranteed optimality for convex cases. Interior point methods dominate large-scale LP due to their polynomial time complexity, outperforming older simplex variants in many practical settings. Nonlinear programming extends beyond linearity, tackling curved objective surfaces. Techniques like sequential quadratic programming, SQP, approximate nonlinear problems with quadratics for iterative refinement. Integer programming introduces discrete variables, complicating solutions significantly. Branch-and-bound and cutting plane algorithms are commonly employed to manage combinatorial explosions. Convex versus non-convex optimization. Convex optimization ensures any local minimum is globally optimal, simplifying analysis and implementation. Algorithms like projected gradient descent thrive in this domain. Non-convex problems present numerous local minima, challenging solvers to escape suboptimal regions. Meta-heuristics like simulated annealing or genetic algorithms are frequently applied here. Statistical guarantees exist for convex problems, but non-convexity often necessitates probabilistic or approximation-based approaches. Hybrid methods aim to bridge this gap. Determining problem convexity upfront is critical. Tools like the Hessian matrix help classify functions, guiding algorithm selection accordingly. Applications across key industries in machine learning. Optimization drives parameter updates during model training. Loss minimization via backpropagation relies heavily on gradient-based algorithms like ADAM or RMSProp. Supply chain management uses mixed integer programming to optimize routes, inventory levels, and production schedules, balancing cost and delivery times effectively. Finance leverages optimization for portfolio construction, risk management, and option pricing. Mean variance optimization exemplifies its application in asset allocation. Engineering disciplines apply these algorithms to design robust structures, minimize material waste, and enhance system reliability through simulation-based optimization. Case study: neural network training. Deep learning architectures depend on optimization to refine weights across layers. Stochastic gradient descent remains fundamental, though advanced variants adaptively adjust learning rates. Regularization techniques like L2 weight decay prevent overfitting by incorporating penalties into the loss function, transforming the problem into a constrained optimization scenario. Hardware accelerators enable massive parallelism, allowing simultaneous updates across millions of parameters, a feat impossible with traditional sequential methods. Benchmarking studies show that adaptive momentum methods, e.g., AtomW, often outperform vanilla SGD in practice despite higher memory demands. Challenges in real-world implementation. Solving large-scale problems often exceed single-machine capabilities. Distributed optimization techniques partition computations across clusters or GPUs. Noise and uncertainty complicate optimization in dynamic environments. Robust algorithms must balance exploration-exploitation trade-offs continuously. High dimensionality exacerbates the curse of dimensionality, requiring specialized methods like randomized coordinate descent or manifold learning. Interpretability becomes paramount in safety-critical domains. Black box models demand additional scrutiny compared to transparent mathematical formulations. Data sparsity, limited observations hinder reliable estimation of gradients or Hessians, affecting algorithm performance. Computational budgets, time/memory constraints force approximations, trading off solution quality for feasibility. Evaluating algorithm performance metrics. Benchmarks assess convergence speed, final error margins, and computational resources consumed. Standardized datasets facilitate fair comparisons across implementations. Function evaluations measure how many iterations an algorithm completes before stopping, serving as proxy for runtime in theoretical analyses. Accuracy is evaluated relative to known ground truths, although this isn't always available for novel or ill-defined problems. Robustness testing exposes algorithms to adversarial inputs, revealing vulnerabilities in edge case scenarios. Common benchmark suites. CIGAR, Combinatorial Integer Global Optimization Algorithm Repository, provides extensive tests for integer programming solvers across varying difficulty levels. The Koinoir project hosts open-source benchmark suites covering linear, quadratic, and mixed integer programs for academic and industrial use. In machine learning, ImageNet and Safar10 serve as de facto standards for evaluating optimizer effectiveness in image recognition tasks. Quantum-inspired benchmarks challenge classical algorithms by simulating qubit behavior, preparing for future hardware advancements. Emerging trends and research directions. Quantum annealers promise exponential speedups for specific classes of optimization problems, particularly those amenable to Ising model formulations. Federated learning applies decentralized optimization principles, enabling privacy-preserving collaborative training across distributed devices. AutoML initiatives automate hyperparameter tuning itself, embedding optimization loops within larger software ecosystems. Multimodal optimization seeks to find multiple distinct optima simultaneously, useful for drug discovery or multi-objective design spaces. Neural architecture search uses reinforcement learning to discover efficient network configurations automatically. Meta-learning trains models to quickly adapt to new optimization tasks with minimal samples. Tools and frameworks enabling modern optimization. TensorFlow Probability integrates Bayesian inference with gradient-based optimization, enhancing uncertainty quantification in models. CVXPY allows users to express convex optimization problems in natural Python syntax, abstracting away solver-specific details. Gecko offers embedded optimization for dynamic systems, supporting differential algebraic equation, DAE, solving alongside traditional static problems. Scikit-Optimize implements Bayesian optimization for automated hyperparameter tuning in machine learning pipelines. Cloud-based optimization platforms AWS Lambda enables serverless execution of lightweight optimization jobs, scaling automatically according to demand patterns. Google OR Tools provides open-source solvers for vehicle routing, shift scheduling, and bin packing problems accessible via APIs. IBM Decision Optimization Center combines prescriptive analytics with enterprise-grade support for mission-critical applications. Microsoft Azure Batch handles high-throughput compute-intensive workloads, ideal for parallelizable optimization instances. Conclusion: selecting the most suitable optimization algorithm depends critically on understanding your problem's characteristics, its dimensionality, continuity, constraints, and desired outcome. Leverage profiling tools to identify bottlenecks early in development cycles rather than retrofitting later stages with inefficient choices. Stay informed about evolving methodologies. Even established algorithms benefit from periodic reevaluation against newer state-of-the-art approaches. Ultimately, mastery lies not just in knowing algorithms but in matching them intelligently to specific application contexts for optimal impact.